Our next speaker is Professor Norm Abrahamson. He's an adjunct professor at UC Berkeley and UC Davis. We know all of his contributions in terms of ground motions and hazard assessment. And as was mentioned by Khalid, he's also the director of the peer research arm on lifelines. Norm?
All right. So while he's pulling that up, the topic here is the future of Geo Hazards, and I could give you my usual, it would be Abrahamson, that one. Yeah. Thank you. In Geo Hazards, if we think of that as the loading from the ground motion, from fault rupture and so forth, this is all changing really fast. Okay, so a lot is happening on this. You've seen me give, many of you have seen me give talks on this before. Key issues of all this are data sets are growing tremendously. As that happens, we are finding out how bad our models really were, okay, and how much things need to change. What I want to focus on, so we're going to have more complicated ground motion models, if you can believe that. We're going to have more reliance on numerical simulations. You're going to see talks on this later on using 3D simulations and how you do that. We're going to be working more on spatially distributed systems and all so forth. But I wanted to go back to what was my previous job at PG&E, and that's actually using this stuff. So how do you get all of these pieces so that they fit together and you can actually integrate them? That's what peer needs to be doing. That's the thing that can only be done in a center. You can't do this with individual researchers. So going forward, while we talk about Geo Hazards, all of this needs to fit into risk frameworks. And so owners of critical infrastructure want to know risk numbers. They're asking for that. The officers of the company are starting to realize there's a risk. They want to know what risks they're taking as opposed to simply meeting minimum regulatory criteria. Okay? That's a different challenge for us to put this all together. Most of the time this is still risk scoring. It's pretty crude, and they're trying to move towards quantitative estimates with uncertainty. The issue is the uncertainties become huge in this business, driven by the uncertainty in the geohazards. So we have to really improve that part of the model. We're not very good at all of this, doing that risk when we're including, I should say, at risk that has dominated by geohazards. When we do geotechnical systems, and I'll use this just as an example here, geotechnical engineers are often taught to be conservative as they do things. I have these numbers, I'm going to choose a lower value of the blow counts or whatever I'm going to do and go forward. That doesn't work when we're trying to do risk. Conservatism and probabilistic risk don't go together. We need things to be mean-centered with uncertainty. That's a different mindset that needs to start to happen going forward. And we're going to get to just the overwhelming uncertainties in risk calculations, again, driven by the uncertainty in the hazard part, which means that's where this is how you make the case for funding. When you can show how bad things are in terms of our answers right now, I've gotten officers to say, this is unusable. I said, yes, that's why you need to fund some work here so we get something usable for you. So again, issues, so as we start to go through this and dealing with how we're dealing with hazards, ground motion models were pretty good at making things mean-centered with uncertainties. Other aspects were not, it just doesn't happen that much. It's not the usual way that things are done. Conservatism gets in, particularly when we start to go to the performance of a geotechnical system. And so this is an example from a dam that's owned by a utility I won't talk about, but we were looking at trying to get risk numbers for a dam and deciding, Do you need to lower water right away? What do you have to do to deal with this dam? So on the x-axis, we had done a lot of calculations of deformation in the dam for different ground motion loading, and then you needed to say, but is it going to fail? And for us, failure here was a wall of water coming down the mountain. Okay, not a little leak, but this is a catastrophic failure. So this is an uncontrolled rapid release of water. And so they went through, and we got our panel of experts, set them in a room and said, all right, if 20% of the crest is lost, what's the chance that it's going to continue and fail? And they gave us numbers that are basically on those blue curves. And then we calculated the risk from this, and on the right-hand side of the table, and we were getting at current water levels, a risk of 1 in 300. This is a really big number for this, and this means you evacuate people right away, you have a really serious problem, you need to lower water. And then the question would be, well, how much do we lower the water? We reran this for, what if they put a restriction on it, 10 feet lower? It only got us a very small improvement in the risk, still completely unacceptable. Then we went back to this panel and said, a cheaper way to, instead of fixing the dam, let's beat up on our panel, right, and get a better answer from them, and said, what really is this? What is this based on? And you're back to, where do people feel uncomfortable? And it was about, if you think, well, I don't like having, if 30% of the crust is gone, I'm really uncomfortable. And people, we figured in the end, are getting uncomfortable at about a 10% failure point, is what we started to try to calibrate the judgment there. Just a small revision to this, or this revision here, dropped our risk numbers by a huge amount, so that if we lowered the water 10 feet, we were at 1 in 12,000 number. That's a number you can start to live with. So the problem that we faced is, how do you get at risk numbers that you can actually use for decision making? And a lot of our uncertainty in all of this is driven by the Geo Hazard side of things. The other place that we get into trouble, we're dealing with risk and the Geo Hazard inputs to this, is consistent treatment of the variability. So risk is driven by variability. It's driven by tails of distributions, and you got to get the variability right. It all needs to be in there once, but only once. Okay, and so here we want to find ways to try to isolate it, but each field wants all of the variability into their piece, right? And they say, I don't care what everyone else does, I got to put all of the variability here. So if we look at something simple, like on the right-hand side, this is just actually just recorded ground motions in a small magnitude and distance range and site condition. And you would say, look, there's all this variability. The black curve there's the average. That's what our ground motion model would produce for the median, and we have this variability. But remember, all of this is in the standard deviation of the ground motion model and the hazard calculation. It's all in there, right? So now when we give that and choose some design level based on a probabilistic calculation, if we now go do site response and now say I'm going to incorporate all the site-specific effects into it, and if I'm doing a good job, the uncertainty in that, well, that variation in site effects was already buried in here. This is back to our problem of our ergodic models. When we lumped all of this together, we get a big variability. Actually, at our site, most of this variability here, so we'd say 70% of the variance, or about a reduction of 40% of the standard deviation, is systematic and repeatable, and shouldn't have been in our hazard calculation to start with. Okay, so we've got things in there too much, have too much variability in there, which starts to overinflate our risk numbers. We get the same issue when we go to time history, so we want to drive time histories into our structure. The structural engineers are going to say, I want all the peaks and troughs in my spectra because it's important for the structural response. And I'm going to say, you can't have it because we've already used it up in the hazard calculation. And so somehow we got to start to partition it. If you need it, this variability, into your structural model, we need to subtract it from the hazard calculation. Get it out of there. There are ways you can start to do that. We could develop GMPEs not for specific period, but for average over a broad period range. We could do 0.2 T1 to 3 T1 or something like that, and then use that average value that will collapse the standard deviation that we run in the hazard, and then you put that back into the peaks and troughs in your time history. But without doing that, we are doubling up on the variability, and we're just not getting the right risk numbers. And we want people to start to use risk numbers to actually make decisions. We've got to address all of these issues. So the other part is sort of level of complexities of the models that we use. Again, an issue on every field is they're going to simplify what everyone else does, and their piece of the model gets really complicated. So we should try to get in our risk calculations some comparable level of complexity in terms of how we're going to do this and not put everything into one case. So examples in dams that I've run into recently. So one way we do this is put all the complexity and make a really complicated model of the dam. We do this sometimes for big structures, big global models of the structure. And they'll say, it takes me 2 weeks to run the model. I'm going to run one time history through it. And I go, well, your answer depends on which time history you use, right? You could either find that it performs great or performs really poorly. But they have a great model for the dam, The other way, so this is my side, right? Many of you have heard me say this. Let's run hundreds of time histories because those drive some of the variability, but now we're going to oversimplify your model. So I'm going to take all the complexity back onto my side and say I'm going to replace your structure by just a nonlinear SDOF or something very simplified. Okay, so we can get all that done but neither of these are really satisfactory by themselves. What's being done now is trying to use these simplified models to choose the time histories, that the small set that you might run into this, but later on we have to try to find some way to balance where we're putting complexity and be sure we capture all of the variability, right? If we do this kind of a model up here, we are missing variability. So we don't want to miss it, and we don't want to double count it. So when we're running, PSHA and Geo Hazards here, when we're running systems other than buildings, Seismic Hazard is driven by the consulting industry here, and we run things that we know how to run, right? So we do it the same way. So we keep running Hazard for elastic spectral acceleration because we're really good at it. We know how to do it, right? But that may not be the right parameter to be using. Okay, we need to start to look at secondary parameters. So if I have an earth structure, I'm going to look at Ares intensity or CAV or PGV or some proxy of a system here. But we need to do time hazard and time history selection based on these parameters that matter, not based on elastic spectral acceleration because it's easy to do, right? And that's really the reason why we do it, that the models are all set up for that. In seismic hazard, the whole concept of probabilistic seismic hazard is that we are summing up all the different ways, all the earthquakes that could lead to damaging motion at our structure. Implicit in that is we are adding up the same thing. Okay, so when we're adding up the chance of exceeding the spectral acceleration at 1 second, what's the chance of exceeding half a G? I can add them all up. That's all fine and appropriate if that's the parameter that's relevant to damage. Okay? If it's not, then we shouldn't be using that parameter. There is no business, we have no right to add those things together so they don't fit together. Okay? So we do this, we run into these problems when we add up stuff from the subduction zone. So we're up in Seattle, we have the interface subduction zone, and we'll have crustal earthquakes. Should you be adding together the rates of them exceeding the spectral acceleration when you're going to come back and tell me their impact on the structure is very different? They shouldn't add them together, but you shouldn't also just analyze them separately because we want to know their combined impact on it. So we've got to switch to start running our hazard for the intensity measures that matter for that particular structure. Okay. So if we're doing changing these to looking for more IMs or different ones, we could be looking at, so most ground motion models are developed for pseudospectral acceleration. So you know that. We have the PRNGA projects developed the new ground motion models for you. These things take multiple years, probably 5 years per time that we do this with multiple investigators. They have a whole lot of stuff that goes into them to be sure that we check how they extrapolate, that they follow physical basis and so forth, and we get reviews of each other, so those things are very well done. Now you want to go to another parameter. Let's say you've decided I want to know Aries intensity, and you go, but I can't wait for 5 years for this group to now work through Aries intensity for us. But there's other ways that, so there are a few models that are developed for these, but the better approach that we want to use for this, we call them conditional ground motion models. And these are going to be using the observed spectral acceleration as an input parameter. So the advantage is that we can use all of the effort that's been built into the proper physical behavior of PSA, but then I can make a model for, here's a model example that I have Aries intensity is some function of, it's got magnitude, and then this has peak acceleration and spectral acceleration. And you can see there's no distance in here. I don't need distance because that effective distance is already captured in the ground motion values. And the extrapolation of this to magnitude 8 at 1 kilometer is already captured in how that extrapolation was constrained in these other parameters where we spent all this time and effort to create them. So we can build these models, these conditional models, that are actually very simple in their form. We're back to easy to look at equations. If I want to worry about hanging wall effects and directivity and so forth, those are all implicitly captured already in these two values here, so that I don't have to go back and create my pages and pages of equations. So we get these physical constraints already, and this is really the key for what makes a good ground motion model. They're simple to develop, very, very robust in their regressions, and if we want to have a full model of this for hazard calculation, we can just combine it with the existing published models for spectral acceleration and get both the median and the standard deviation of the resulting model here in an easy way. So that means I can go grab the 5 NGA models here, combine them with one model for Aries intensity, and I could create 5 models, and so I would now have the range of models that I might need to have in hazard to calculate propagate the uncertainties. If we look at what's starting to happen here, this is an example of hazard done in spectral acceleration up in Vancouver. In this case here, we're looking at 10 to the minus 4. They are dominated by the shallow crustal earthquakes at short periods, and the interface is only about 10% of the hazard. If we use those conditional models and then now just turn every one of those GMPs that we used before into an Aries intensity one, so I had the full range of epistemic uncertainties, we can see what happens here, and this is a flip, right? So the interface is now dominating the hazard. Here's a contribution, so if I use that, I've got 60% of the hazard is from interfaces as opposed to 10%. The issue we have when we start to deal with fragilities and risks and so forth, if we're thinking about these numbers here, the deaggregation on spectral acceleration does not represent what's happening in terms of what's controlling your answer. So you shouldn't go say, well, this is what's controlling the hazard, so I'm going to make 60% of my time history is crustal and only 10% of my time history is interface, when interface is the controlling answer. Okay? The other problem, though, if we just do this, if I said, well, crustal didn't matter or slab didn't matter, only interface matters, I shouldn't have been scaling it up to this value here. We had no business adding these things together. They're not the same. Okay, so it's cleaner if you just jump to a parameter that matters. So we can easily make these hazard calculations for a parameter here that matters. What's shown on the right is making a simplified proxy for the deformation, actually calculating deformation hazard. It's a little more involved, but a similar thing here. And you can see that now we're getting contributions and shapes from our IM that we think is related to damage or deformation. That is actually much closer, right? So you can start to get the relevant numbers. If we don't do this, the risk calculations are not going to be right. Okay? The handoff as well between seismic hazard and the geotechnical engineering steps here are an issue. Right now we use VS30 as a handoff. We need to make everything fit together when we're going to run risk. The loading conditions, the hazard calculation, the ground site response calculation, and then the structural response, right? But this is not a fundamental parameter of the site response, and it's turned into that by default, because that's what people say, I stick VS30 into the GMPs, that must be what matters. VS30 doesn't matter at all, right? The only thing that matters is the velocity profile, and that velocity profiles tend to be correlated in natural deposits with VS30. So we really are going to need to move to handing off things properly so that there's consistency in how the results are done. So if we look at, this is a plot some of you have seen before. Greg worked on this, a student. This is velocity profiles that have the same VS30. This is the average profile in California. It's a solid black line. This is the average profile in Japan. And then this is the average profile in Seattle. These are deep. This is 6 kilometers. Okay? So you're used to working up here. But if you want to know long period response, it's going to be affected by what's happening at deep depths. So VS30 isn't telling me what's going on. If I grab a ground motion model from Japan and say I'm going to apply it here, then I would end up running my analysis and saying, this is how I am assuming, or that model assumes this is a velocity structure that you have there. So we need to have these consistent. So finally on to risk and why Geo Hazards controls our risk calculations. This is for dams, and this is one way dam people work is fatalities and annual probability, so they do put deaths on here, and they have a target line. If you're above the line, it's bad. If you're below the line, it's good. This is for dams in Northern California, and this is our uncertainty estimates in the hazard calculation, and this is the uncertainty estimates in the fatalities. But if we move to non-ergodic ground motion models, meaning we need to explain what is systematic and repeatable, you're going to hear talks about this. This is our uncertainty range. It's bigger than the plot, right? So I've shown this to decision makers, and they go, this is useless. They say, yes, but if we collect the right data and do the work, we can reduce that. So there's big uncertainty and risk is really a problem. What do you do with it? Right now, we use the mean risk. The mean back here is this dot. This dot I could be really safe down here or really unsafe. And I need to do more than the mean. So the mean is not nearly enough. Okay, what should we be doing? We need to tell people and communicate the uncertainty of what we're doing. Once the size of this uncertainty is understood, the business case is suddenly made for why do they need to fund the research and move things forward. Okay, so summary, we need to have consistent way of handing off information to get from all of these pieces to get consistent risk numbers. How do we better understand how these systems actually perform, particularly geotechnical systems? Not a conservative approach, but what's their expected behavior and aleatory variability? And then what do you do with these large uncertainties and risk? Okay, thank you.